What is a machine shop but a set of tools used for making more tools for a machine shop? It's a vicious cycle, one that I'm already getting sucked into. When I inherited my grandfather's machine shop, it came with a full set of 5-seat collets. These are excellent for repeatably holding small round workpieces in the lathe or on the mill, for instance. Now, while the mill and lathe are all cleaned up and ready to make parts, basically everything else is still a mess. This collet set included. But I'm going to ignore that fact and dive into making something anyway. What am I making, you ask? Well, how about some collet blocks? This should be interesting. Collet blocks usually come in hex and square designs and are useful for holding small round parts in your mill vise. The shape makes it possible to quickly index either 60 or 90 degrees just by rotating the block in the vise, so you can easily mill a square or a hex on the end of a shaft. Sure, I could buy the pair for $50 online, but why would I do that when I can spend a mere 40 hours designing them and making them myself? This should be a good starter project to get the old machine juices flowing again. I just have to avoid getting pulled away on too many side projects. Before I get to making these, I need to come up with a plan. Most of my work as an engineer is done in 3D modeling software. But for this project, I'm looking for a break from that and going back to the drawing board, literally. It's been over a decade since my last high school drafting class, but it didn't take long for some of that old knowledge to come back to me. There's something therapeutic about creating a physical drawing. It's like creating a work of art. The final design will consist of 4 parts that I would need to make. The body for holding the collets, an anti-rotation pin that sticks through the body, engaging with the collet preventing it from rotating, a locking ring that threads onto the end of the collets which secures the workpieces, and a retaining screw that will keep the locking ring attached to the body. Oh, and I will be making 2 versions, a hex and a square. To keep this on the cheap, I'm only using materials I already have in this shop. This mystery steel for my stockpile should do the trick. I have my design, I have my material. Let's get to making. I'm starting with the lathe operations, but unfortunately the spindle bore is not large enough to hold this entire length of stock, so I'll have to cut it down to more manageable pieces. I don't have one of those fancy horizontal automatic feeding bandsaws, so my vertical one will have to do. Not perfect, but this will get me by. Stay on task. I'm cutting the stock about a 1/4 inch longer than my final dimensions. This will not only give me material to clean out both ends, but it will also potentially save me if I goof on the first end. With the stock cut to size and chucked up, the first operation is to cut the collet side of the body. Let's start with facing the end. A single deep pass at moderate feed rate is enough to clean it up. Then a shallower pass at higher RPM gives me the final surface finish. Next I can move on to the diameter. I only need to take off about 1/8 of an inch, so a couple heavy passes clean up the bulk of the material. Then one lighter, more accurate pass. From here I can measure with the micrometer and re-zero the DRO. Doing this after a light cut helps ensure the deflection and cutting ridges aren't throwing off my measurements. From here I take a few more light cuts and hit the target diameter dead on, or within a couple tenths anyway.
Let's say good enough.
With the outside to size and the end faced off, we can now drill the through bore for the collet. First starting the hole with a center drill, I can move up to a 1/2 inch through the full depth, then jump to a 1-inch drill. My target is 1.25 inches, but this is the largest drill I own. The rest of this will need to be done with a boring bar. I'm only setting the boring bar out enough to clear the back of the stock. This should help keep vibrations down and give me a smoother cut. Get it together, Butterfingers. I'm also setting the height of the tool a hair above center. This should help prevent overshooting the diameter as the bar deflects downward under load. The collets have a 10-degree taper, but from what I can measure on the other collet tooling in the shop, the female receiving taper is 9 degrees. My guess is that this ensures the clamping forces stay on the end of the collet, giving it the best holding power. So I'll match this and set the compound rest to 9 degrees as well. Alright, now we can start boring. Except that sounds awful. After too much time messing around, it turns out the boring bar is a lot happier feeding out of the part rather than in. With that figured out, I take several passes and ease my way to the final diameter. Using the compound we previously set at 9 degrees, I can cut the taper. There's no power feed, so it's all on me to make the finish look good. Not too shabby if I do say so myself. Last step is to chamfer the edges. This wasn't in the original plan, but chamfers are sexy, and will make the finished part look a lot better once the flats are milled. From here, it's just rinse and repeat on the second body. If you remember, I want both square and hex blocks, so I'll have to turn down 2 separate bodies that I'll mill down the final shape later. That's the first part of the lathe operations finished for the bodies. Now I need to turn the other ends. But for these, the bores on both ends need to be as concentric as possible, which is a perfect job for a 4-jaw chuck. Mine eluded cleaning during the lathe restoration, so let's get this cleaned up real quick. This should only take a minute. That looks much better. The magic of the 4-jaw chuck is that each jaw can be adjusted independently. This lets me incrementally move the center axis of the part until I'm perfectly in line with the side I cut first. In theory, this is pretty simple to do with a dial indicator. The reality is it's a little bit finicky.
This totally doesn't matter, but I want this cleanup pass to line up with this one seamlessly. So let's make some cuts.
Like the collet side, I'll start by facing the part to length and turning the outside diameter. Again, these dimensions aren't critical, but practice makes perfect. The inner diameter of this receiving bore is actually critical, though. This will not only keep the collet centered when in use, but also make the locking ring action buttery smooth. Now that I'm adequately warmed up on the lathe, I'm feeling a bit more confident on starting the locking rings. These have a variety of complex features, so this should be fun. Since the finished part length is relatively short and all the features can be cut from one end, I'll switch back to the 3-jaw chuck. The first few operations here are similar to the block bodies. Face off the end, then turn down the outside diameter. This part has a reduced area where it slips into the bore of the body. The ring diameter is about 1/1000 smaller than the bore we turned in the body, and this gives a perfectly satisfying slip fit. Onto the bore. There are a few different diameters here as well as some internal threads. First, I drill out most of the material to within a 1/16 of an inch of the smallest diameter, and then take the ID to final dimension with the boring bar. While I'm in here, I'm also going to bore out the section for the threads. Now for something a little more advanced. I need to cut a little window at the back of the threads to give myself an 1/8 inch stopping area for the threading tool. While I'm in here, I'm also going to cut a nice little internal taper between the 2 diameters. Because I can't see any of this, I'm having to rely entirely on the DRO and hand wheel dials to perform my maneuvers. And if I can't see what's going on, you definitely can't either. But trust me, it all worked out fine. Now I'm ready to cut the threads. Did I mention this will be done blindly as well? Time to muster up the nerves of steel. Since I'm essentially power feeding the threading tool into the bore blindly, I'm going to do myself a couple favors. First, I'm running the slowest speed this lathe can go. This isn't preferable for surface finish, but I really don't want to risk crashing. Next, I'm resetting the DRO at my stopping point inside the part, so I only have to look for a 0 rather than some arbitrary number. Alright, everything is set, let's do this. I'm taking about 5 thou passes on the radius using the compound rest already set at 60 degrees. This causes the tool to only cut on one edge, which to my understanding results in a better cut than using the cross slide. I know roughly how far I need to go, so when I start to get close I use one of the collets to test the thread. Perfect. The last feature on this part is the groove for the retaining screw. If you remember from my initial design, this retaining screw ensures that the locking ring and body don't get separated. I don't have a grooving tool ready to use, so I'm going to use this smaller parting bit. As long as I only do penetrating cuts, I won't be putting any side load on this tool and the accuracy should be okay. Perfect. Now I can just part the piece off a little long, face the other end of dimension, and start over. Fortunately, with all the setup figured out, I was able to knock out the second ring pretty quickly. That's all the turning complete on the big pieces. For the few smaller pieces of hardware, I'm taking the 3-jaw off and using the collet chuck. The drawbar mechanism for this is another one of those loose ends that slip by during the lathe cleanup. But I just can't accept putting this dirty mess of a contraption on my freshly cleaned machine. Alright, with that up to snuff, I can start. The The first pieces of hardware I need are the anti-rotation pins. These are the pins that stick through the body and prevent the collet from turning as I tighten the locking ring. The slot in the collet is an 1/8 inch wide, and luckily I have some 1/8 inch round steel. I am, however, going to face and turn down the end just a few thou. This should help ensure the pin engages with the slot smoothly and doesn't bind. This is a relatively small diameter, so I have the gearbox set at the highest speed. 2000 RPM doesn't sound all that crazy until you're hunched over the screaming spindle. After cleaning up the rest of the length with a whetstone, I can just cut it off with a hacksaw. This end will get milled off, so I'm not worried about surface finish here. The final operation on the lathe is to make the retaining screws. For these, I'm starting with a couple 1/4 20 button head screws. I need to turn down the ends to a pin feature that rides in the grooves I cut in the locking rings. But of course I have no way to hold these screws in the lathe to turn them. So in true machine shop fashion, I will have to make a tool. I'm using a 1-inch length of bar stock with a threaded hole, but first I'm boring most of the inside away with an end mill. This will give me the proper amount of stick out for the screw, but also give me enough material to hold on to in the collet chuck. Mounted in the lathe, I can cut most of the screw down to length with a hacksaw, then finish up with the cutting bit. I will need to make the cuts while running in reverse to prevent the screw from backing out. But of course my lathe doesn't want to comply. Hold please for a completely unavoidable detour. Okay. Found the problem. This cam that actuates the switch for running the lathe in reverse was just a little bit off. I guess it could have been worse. Alright, where was I? Right, turning down the screws. I want the end to be about 5 thou smaller in diameter than the width of the groove on the tightening ring. This will give me enough clearance to let the ring turn freely, but also not be so loose as to be sloppy. And with that, we're done on the lathe. We made the bodies with both the tapered collet end and the locking ring end. We made the threaded locking rings to slip fit into the bodies. We made some anti-rotation pins to hold the collets. And finally, we squared off the ends of the retaining screws. Now it's time to do some milling. Most of my time here will be spent cutting the flats on the blocks. So I'm going to rotate the vise 90 degrees and let my x-axis power feed do all the work. With the vise trammed in, I can set up the first block. I want the flats to be as parallel to the center bore as possible. So I'm using a dial indicator to help set the height on each end. A face mill is perfect for this operation since that's basically what I'm doing, facing the material. I want to make sure I don't overshoot my cut depth, so I'm finding the part height by hand. From here I can zero the knee handwheel dial, set up for a 20 thou pass, and let her rip. I'm leaving about a thou or two extra material on the body just to give myself some wiggle room for finer adjustments later if needed. I can use the flat I just milled and a bevel protractor to set up the second and third passes. If you couldn't already tell, this will be the hex block. The last 3 sides are simpler to set up. I can put the milled face down directly on the vise and then just cut the top. A mist coolant system would be perfect for this situation. I have one, and I even spent an hour trying to get it to work, but no beans. So squirt bottle it is. The square block is the same process, but instead I'm using a precision square for the setup. Then it's just a bunch more face milling. Thank goodness for power feed. I'm going to go ahead and cut some wrench flats on the locking rings while I have the facing tool mounted. My original plan was to mill slots on the perimeter for a spanner wrench, but then I would have to make a spanner wrench. Just another thing to keep track of. So instead I'll just mill 2 flats through this 1 5/8 wrench I already have. That will work perfectly. Before I move on, I want to inspect the dimensions of the flats I just milled on the bodies. Time to get reacquainted with the surface plate. Key feature of these blocks is that they're symmetric around the center axis of the collet. So I need to mount something in the center to act as a reference point. The shank of this end mill should do the trick. I can set a height gauge with the dial indicator to the theoretical height the top of this shaft should be. Then get a reading on both ends of the shaft. This will tell me how far off center each face is, but also tell me how parallel the center axis is to those faces. I'm seeing some minor deviations, but no deal breakers. This is where the good news ends. When checking the face angles, everything was coming in within 5 arc minutes of the spec, until I measured one of the flats on the hex block to be 20 arc minutes off. That gap between the protractor and face? Yeah, that shouldn't be there. Sheesh. I must have knocked something out of whack when setting it up on the mill. Rather than try and fix this now, I'm going to wait until I have the surface grinder up and running, and dial all the other dimensions in at the same time. Even with this little mishap, these will still be usable for small parts where the error won't translate to anything substantial. So I'm going to keep going. The final operations on these blocks are a couple holes for the hardware. For the anti-rotation pins, I'm drilling an undersized hole and reaming it to a -1 thou press fit. A quick hone on the inside to clean up the burr, and I can very slowly tap the pin in. I basically only have one chance to get this right. I can't overshoot my mark or the collets won't go in and I won't be able to back the pin out. I could probably go a little further, but I won't push my luck. I'll trim this down most of the way with an end mill, then clean up the rest in a minute. While in this setup, I need to cut the hole for the retaining screw. First is the center drill, then pre-drill for the tap. Do the tapping, and finally cut the counterbore with an end mill. The final machining operation is to take a skim pass on this face. If I do this right, the pin we hammered in earlier should disappear. Like that. Alright, let's get these cleaned up for final assembly. The locking rings are a bit finicky to get into their bore, but once in they spin so nicely. Next, the retaining screws. If the position of the hole isn't just right, it would either cause the locking ring to bind or not let it seat against the back of the block. Looks like it's bang on though. Man, I could play with this all day. So how does a collet fit? That is nice. Let's take this for a spin and see how it does. Easy now, it doesn't count as a detour since the project is already finished. I'm curious to try the hex out. In theory, I should only have to set this up once. Then I can just index the block in the vise. Okay, that looks pretty decent. But the real test, how does it fit? Not bad at all. See, I knew this would still be usable. While this was a fun project to dive into, I definitely uncovered some parts of the shop that still need some attention. Before I start on the next machining project, I have a few things I need to get in order. See you next time. Thanks for watching.